In March 2022, the School of Medical and Life Sciences organised an event with Mike Meredith. He will give a brief overview of the history of data analysis and statistics and share what's new in the data analysis toolbox for biologists.
Welcome to this seminar on data analysis. Today we have Mike Meredith, a very close friend of mine. He's going to talk to you about what's new in the data analysis toolbox for biologists. And I knew Mike for how many years now? Maybe 5 years now. But Mike has a history in developing statistical packages. That's why he's here today. He's giving us a 1.5 week workshop with students, staff, and people from all around the region. He's been here for close to maybe 10 days now. And
halfway through, so a week, huh?
Just
over a week.
Yeah, and he's here today to give us a very special lecture on what's new in the data analysis toolbox for biologists. So the workshop was mainly for wildlife ecologists and biologists, but today he's going to talk a bit about what else biologists can use. A lot has happened since the days of Fisher and Reverend Bayes, and today is going to illuminate what's the latest statistical packages that you can use for analysis. And Mike actually has a master's in natural history from Cambridge, natural sciences from Cambridge. He got a master's in arts, and he also did his MBA in Durham University, and he also has a master's in environmental management in Y College, which is now bought over by Imperial. So he's an alumnus of the Imperial College. And Mike has a very interesting history. Mike used to be working for the government, the Sarawak government. He was a manager for the Mulu National Park. And since then, he's also gone on to work for the Wildlife Conservation Society. And during then, he developed interest in statistics, and finally decided to make that his one of his life's purposes, to try to share knowledge on statistics with wildlife biologists, because we realized that a lot of wildlife biologists were not really doing good statistics, proper statistics, and we were losing a lot of information, and we wanted to. Mike's got a lot of new techniques to allow wildlife managers to do better at managing wildlife. For example, he's going to talk a bit about how Bayesian methods can provide biologists a very interesting, very important way of finding out what the probability, for example, your interventions are working, what the probability in which your population is increasing. So all these are more useful for decision makers rather than the usual, p-value, significant, not significant. So Mike's trained out a whole army of wildlife statisticians, in the sense of all of us are now clued into the latest in statistics. He has done over 45 boot camps across 11 of our countries, and more than 720 participants have joined his boot camps all around the world and the region. So Mike's trained up a lot of scientists like me. I have been to 4 boot camps before, and this is, unfortunately, I don't have time anymore to attend any of his boot camps. But I owe my knowledge in statistics to Uncle Mike. We call him affectionately Uncle Mike. And Uncle Mike today is going to share with us what's new for biologists in the data analysis toolbox. So take it away, Mike.
Good. Yes, thanks very much, Ruben. I'm not really a mathematician or a statistician, though I must say I was interested in maths. I was especially interested in maths in high school, but I insisted on doing physics, chemistry, biology, and maths. And the system wasn't organized for that, because if you're a biologist, why do you need maths? That was at the time in the 60s, that biologists didn't need maths. That's no longer the case. Biologists definitely need maths these days. And my main interest in this sort of analysis, wildlife analysis, came from WCS, when the director of WCS, Navin Kumar, his concern was that we were not producing enough information for managers from our data collection. So we started thinking, how can we best do this? How can we get more information? How can we get more information from our data, which would be useful for managers? And my background then was management, managing Mulu National Park, preparing management plans for new national parks, training rangers, all that sort of thing. So my background was in management. So yes, the idea that we should get more out of our data, which would be useful for managers, that was good. So we gradually developed that over the years, and the result now is our boot camps that Ruben referred to, and we also do more advanced workshops, and quite a large number of our alumni have now gone on to do degrees, masters and PhDs, which involve data analysis. So yes, that's not really what I'm here to talk about. What's new in the data analysis toolbox? Okay, let's start off with a quotation. Statistics is in a stage of rapid evolution. Lots of new statistical methods have been marketed. I like that idea. People have been promoting their methods. And practitioners who've not kept up with this can find themselves a little bit at a loss to know what's going on. That was written by George Snedecor in the introduction to his statistics textbook in 1937. So this is a little bit of a retrospective. The same thing I think applies today. Yeah? But let's have a little bit of a retrospective and see what George Snedecor, the late George Snedecor, was talking about. What happened between 1917 and 1937? Lots of things were happening. It was a very revolutionary time. Huh? Fisher was at Northampstead Experimental Station, and he developed the ideas for experimental design, replication, and randomization. And that really is the basis of what people do today. Previously, people were just taking a whole field and putting fertilizer on it and seeing if it produced more oats or whatever than the previous year. Fisher said, no, we must have replica plots and we must randomize, and then we can make causal inferences. So experimental design and hypothesis testing. Fisher didn't invent hypothesis testing, but he formalized it, and the idea of a p-value as strength of evidence. He also developed the idea of maximum likelihood estimates, which is still very much part of the frequentist methods that we use today, i.e. non-Bayesian methods that we use today, and ANOVA and regression. He didn't invent regression, but he did do a lot of work to tidy it up. On the other side, there's the work of Neyman and Pearson. They came up with a rule for deciding between two hypotheses, where you would decide which hypothesis you were going to go with, and not be wrong too often. So there's ideas of an error rate, and you decide on the error rate for accepting different hypotheses. And then also around that time, a little bit later than the Neyman Pearson work, Neyman introduced the idea of a confidence interval. So all of that was going on in those 20 years prior to 1937. And it really was a very active period for statistical evolution. Don't forget that people in those days, most statistics was done with pencil and paper and tables. You calculated your t statistic or your f statistic or your chi-squared or whatever, and then you looked up in a table to see what the p-value was, or at least the range it was in. It was not possible in those days to actually calculate a p-value. That was a huge amount of work. So you just looked it up in a table and said, oh, it's less than 5%, or it's less than 1%, or whatever. If you were lucky, you had a mechanical calculator, which could do multiplication and division. And if you were really lucky, you had a computer. And a computer in those days was usually a woman, a young lady who operated your mechanical calculator. So those were the first computers in the 1930s. Okay, from 1937 onwards, null hypothesis significant testing became the norm. It's not really Fisher, it's not really Neyman Pearson, it's a sort of a mishmash of different ideas. And P less than 0.05 became a requirement for publication. You can't publish if your p-value is 0.06. The journal won't accept it. And of course, if there's no p-value, then you can't even, they won't look at it. Okay, so significance tests became sort of magical incantations. This is what you need to do to get your papers accepted. And right at the beginning, there was criticism of this idea. Yates, who was a colleague of Fisher at Hampstead, he was complaining that researchers were just looking for significance and they ignored effect size. So this is Agricultural Research Station, the effect of fertilizer on the yield of oats. People want to know if it's significant. Well, that's not really the point. If you're a farmer, should you put fertilizer on your oats? What you want to know is the effect size. And Yates and many other people were quite critical of this significance and focus on p-values, as was Fisher, in fact, in some of his later writings. Okay, so p-values are very important. Let's have a quick look at p-values. What does it mean? P-value is the probability of getting the data. Getting the data that we got, given that the null hypothesis is true. The p-value is not the probability that the null hypothesis is true, given the data. That's a common misconception. Many people think that the p-value is the probability that the null hypothesis is true. Sorry, that's what we want to know. The p-value doesn't tell us that. Okay, there's those few dots in the middle. Those are important as well. Our definition isn't complete yet. P-value is the probability of getting the data we got, or more extreme values if the null hypothesis is true. And that more extreme values can sometimes be a bit of a problem. It's a problem, for example, if your sample size is not determined by the researcher. If your sample size depends on how many people volunteer, then you could have a different number of people volunteering. And then you need to think what more extreme values you could get if more people volunteered or if fewer people volunteered. And that becomes very messy. Yeah? In more straightforward cases, there's something called the stopping rule. When do you stop? Suppose we're worried about the number of, or the proportion of females in turtle hatchlings. The sex of turtles depends on the temperature of incubation of the eggs. Higher temperature of incubation, higher proportion of females. Global warming. Is this happening in the wild? If so, what are the consequences for turtle populations when these hatchlings become adult and they want to breed and they're all females? There's no males around. So, okay, we do a little study. We look at, somebody looks at 13 hatchlings. You can't just flip them over and look between their legs. That doesn't work. You have to actually kill the little fellas, dissect them, and look under a microscope. So, done this with 13, and there were 10 females and 3 males. Is the difference significant? Yeah, what's the p-value? If you intended to stop at 13, if the idea at the beginning was that we're going to do 13 and then we'll stop, then what is more extreme? More extreme is 11 females and 2 males, 12 females and 1 male, 13 females and no males. And in that case, the p-value is 0.046. It's significant, we can publish. Great. What would happen if instead of saying we're going to investigate. We're going to stop at 13. We're going to stop when we've got 10 females. So what's more extreme? 10 females, 2 males, 10 females, 1 male, 10 females, 0 males. On that basis, the p-value is 0.57. Look, not significant. Or we could decide to stop at 3 males. More extreme then would be 11 females and 3 males, 12 females and 3 males, 20 females and 3 males, 100 females, 1,000 females. Those are all more extreme. On that basis, 0.092. Or we could decide to stop when the difference is 7. Okay, then more extreme would be 9 females and 2 males, 8 females and 1 male, 7 females and 0 males. 0.087. So exactly how you do this, if you decide, right, we're going to work with 13 animals right at the beginning, then we can do everything nicely. If you don't decide, you have other stopping rules, then it's all very complicated. Yeah, and the p-values are different. This is not a problem with Bayesian methods, which I'll be talking about later. We'll see how we can do a Bayesian analysis with these same data. But the frequentist approach, we are thinking of being able to do the experiment many, many times, and the results which you might get in these many replications of the experiment. And that's the basis of the frequentist paradigm. Okay, so let's move on now to 2022. We are no longer using mechanical calculators, pencil and paper. I don't know. I have difficulty writing these days with a pen on paper. I'm so used to using keyboards and things. But now we have computers, we have powerful software, we have GPS so that we can get accurate locations. We can stick GPS collars onto animals and get information about where they go. We have mobile phones, and lots of people now are entering their data in the field directly into their mobile phone, and then it can be uploaded to the computer. So there's lots of things going on. We're in a different world, huh? To the world of Fisher and Damon and Pearson. Okay, so what's happened now during the last 20 years, at least in wildlife biology, there's been a renewed focus on models. Models with many potential effects. So we're not looking at single effects, the effect of fertilizer. We're looking at many effects. Some effects are large, some are small. And then we do model selection. We have multiple models. And we do model selection with AIC. And we also can take account of imperfect detection, which is a problem in wildlife research. And the other major thing which has happened is the introduction of Bayesian methods in ecology. This provides better information for management. That's a major concern. And going back to our original idea that we need to produce in our data, we need our data to be useful for management, Bayesian methods became important. And the bugs language now makes it relatively easy to use complex models, or to analyze complex models. We'll look at this in more detail. Going a little bit more than 20 years ago, 1997, the ecological detective, Hilborn and Mangon, the subtitle is Confronting Models with Data. And the idea was that you generated multiple models based on ecological theory, ecological hypotheses, and then you compared each of these models with the data which you'd collected, and then you decided which was the best model. And in those days, they had 3 ways of deciding which was the best. One was the likelihood ratio, something which Fisher would recognize. Akaike's information criterion, which came out in the early 70s, or Bayesian analysis. But the Bayesian analysis was very restricted. Okay, a little bit later, Burnham and Anderson came out with a book on model selection and multimodal inference, and they pushed the idea of AIC, Ake-Ike's information criterion, as a way of selecting the model. The theoretical deviation, the derivation goes back to Kuvat-Liebler information theory. It's all very theoretical and mathematical. The lowest AIC is the model with the lowest AIC is the one which is nearest to the truth. Well, that's all very well in theory. From a practical point of view, the lowest AIC is the best model for making predictions. It's actually equivalent to cross-validation. So if you want to predict some value of a parameter, then it's best to use the model with the lowest AIC. When I say predict, I don't necessarily mean we're making forecasts. It could just be that we have a site or an individual, an animal or whatever that was not included in the sample, but we want to know something about its survival based on covariance or whatever we want to do. AIC is implemented in standard software that we use in wildlife biology. Distance, mark, presence, density. That's become the standard, and it's also widely used in other disciplines, in engineering and business and so on. In 2006, the Ecological Society of America had a special section in their journal Ecological Applications entitled The New Statistics in Ecology. And the new statistics were models and model selection using AIC. So already in 2006, ecologists were moving away from NHST, hypothesis testing, and going on towards model selection. The next thing which happened in our little world, 2008, a book by Royal and D'Orazio, Andy Royal and Bob D'Orazio, Hierarchical Modeling and Inference in Ecology, where they introduced Bayesian methods. They used Bayesian methods and frequentist methods, frequentist i.e. non-Bayesian. The idea behind Bayesian analysis is not new. It goes back to Thomas Bayes in the 1600s, 1700s, sorry. It was actively used, it was used extensively by Laplace in the early 19th century, but it fell out of favor. The frequentist party took over. People decided that frequency was the proper definition of probability. However, more recently it was used by Crone in 1996 because they wanted to produce straightforward probability statements to give to government. Wade already in 2001 showed that Bayesian results provide better information for decision making. But the real problem until 1997 was that it was really difficult for anything more than a very simple case to actually do the calculations. For very simple cases with one or two parameters, it could be done. But once you get more than a couple of parameters, it was not possible. It was infeasible. What happened in 1997 was that the bug software package came out. It had been developed by the Medical Research Council in the UK, or financed, and their statistics unit at Cambridge. They produced this, they've been developing this for 10 years plus, and it was released in 1997. The bugs modeling language and software made it easy to write code for complicated models. And it was realistic. We'll have a look at a piece of code in a moment. You could have separate models for ecological processes and observation processes, and you could use prior information, which I think is what the Medical Research Council was interested in. That they could actually accumulate knowledge as time went on. Whereas Fisher would have said you have to throw away all your old information and start again when you do a new experiment. Okay, so this is an example of a model in the bugs language. So we have at the top, we have the ecological model, Z, Z. For each site, it's either 1 or 0, depending on whether the species is present or absent. And that doesn't depend on whether you detected it or not. If you detected it, then sure, it's present. If it's, but it might be present and not detected. That's based on Bernoulli distribution with psi, which is the probability that a site will be occupied. Then we have the observation model. Y is the number of observations at the particular site, number of times you saw the species. N is the number of times you looked. And P is the probability of occupancy. Probability of detection. And then we have some priors. In this case, we've got uniform priors between 0 and 1. And we can get out N is the number of sites which are occupied by the species. So that's a simple, straightforward model. It makes like ecological sense. Each of those statements there is a statement about ecology, what's happening in the field, and that's a good way to work. Bayesian modeling also allows us to use hierarchical models. Our little occupancy model actually is hierarchical. We've got the data. Let me just back up. We've got the data is Y, and the observation model is about the data. If the site is occupied or if it isn't, we get different values. So Z there, and Z is controlled by another model which is higher up in the hierarchy. So this is already a hierarchical model. We can use random effects, and we can share information among sites or species when data is sparse. So for example, in the National Tiger Survey, there are sites there where there was only one tiger captured. With n equals 1, there's not much you can do in terms of analysis to calculate probability of detection or to calculate how many tigers there might be there. But when work is being done, when data is being collected in a whole series of sites across Malaysia, Peninsular Malaysia, then we can borrow information from other sites to actually analyze the data for this site, which has only one detection. And in fact, there was one site with 0 detections, and we could work out the probability that there might be a tiger in there, which had never been detected. And that we can do with hierarchical models and putting your data from different sites all in together. The other thing which we can do easily is multi-species models. We have many species of birds, many species of mammals, perhaps. And for some of these species, we have very few data. Data are very sparse. But if we put them all into a model with other species where we have lots of data, we can borrow information, share information between the species. Okay, that has led to something of an explosion in hierarchical models and this kind of analysis. Textbook Applied Hierarchical Modeling in Ecology. Volume 1 that came out in 2016, and your colleague Ravinder used methods from there for her PhD. The second volume came out in 2021, and another book with lots of good models using R and using Bayes, integrated population models, that came out. It's dated 2022. It came out in November last year. So there's lots and lots of papers now using these methods. It's really, really important in wildlife ecology. Obviously, these things are actually quite advanced and they're not simple. No? I've been involved with these books because I've been looking at the code and making sure that their code is okay. And there are packages for both of the books, for the 2-volume Applied Hierarchical Modeling and for integrated population models. which are my responsibility. Okay, so that's right up at the top end, as it were. People say that that Bayesian methods are really complicated. It's difficult. It's advanced. You need to have your degree in mathematics first. I don't think that's true. Right? So, Bayesian probability for babies. That's a book which is available, and it explains the very basics of Bayesian probability. That's perhaps a little bit too. It doesn't go far enough, let's say. So there are other books coming out now. Increasingly, in our workshop, we introduce Bayes' rule on day 2, and then we don't talk about frequentist methods until day 4. So Bayes first. And there's increasingly a move to start with Bayesian methods from scratch. And Student's Guide to Bayesian Statistics, this is aimed at undergraduates. This is in that tradition. I think that works because Bayesian methods are more intuitive than frequentist methods. If you think frequentist methods are intuitive, then maybe you're misunderstanding it. The p-value is not the probability. The null hypothesis is true, though perhaps intuitively it should be. Bayesian methods do actually match your intuitions. Going a little bit further, there's Statistical Rethinking, a nice book by McElrath, which rethinking because it's moving away from frequentist methods towards Bayesian methods, and then doing Bayesian data analysis, practical things about how you do it, how you program, how you write the models, by John Krushka. Okay, so if people are happy with what they're doing with hypothesis testing, where do we go next? There are Bayesian alternatives to NHST. The advantage of a Bayesian approach, even for simple things where NHST actually works, is that it allows probability estimates of your parameters. We get a full probability distribution, and we don't have to worry about alternative results that we could have got but didn't. So if we go back to the hatchling data, 10 females, 3 males, the Bayesian approach, we don't have to worry about what we might have got and didn't. Bayes, we look at the data and we work with the data that we got. We don't have to worry about replicate experiments and what we might have got instead of if we replicated it and so on. We can work just directly with the data which we have. And if we plug that into the Bayesian estimation routine, then this is what we get. It's a straightforward binomial problem, so that's all right. We get an estimate of the sex ratio. Our best estimate, a point estimate, is 0.73 for females. We get a Bayesian credible interval, and we can say that we are 97% certain that the sex ratio is more than 50-50. Yeah, there's more than 50% females. Yeah, whether 97%. 97%, yes, that's okay. Two-tailed test, that's all right. That would be significant. Okay, and we don't have to worry about the design. T-test, Bayesian alternative to t-test. This is John Krushka's hobby horse. He produced a paper in the Journal of Experimental Psychology back in 2013, saying that Bayesian estimation supersedes the t-test. And it was the best software that came with that, and which I turned into an R package. So let's have a look. This is an example, an ancient example from 1908, I think, when Student was putting forward his idea about t-tests. And he was using data for 2 soporific drugs, 2 drugs which would make people go to sleep. Which was the best, and this is just for drug 2. Right? drug 2, 10 individuals, 10 subjects. How long did they sleep without the drug? How long did they sleep with the drug? How many extra hours? And if you do a one sample t-test, then it comes out as being quite significant. Okay, let's put that into the best package. And we get a mean of 2.3 hours difference. And we get a nice posterior distribution, and we get a Bayesian credible interval. And we're 99.5 certain that the mean effect of the drug is actually positive. Okay, but what we're interested really, as usual if you want to evaluate a new drug, you don't want to know whether it works, you want to know whether it's more effective than the existing treatment. So students compared his drug 1 and drug 2. That's really what he was interested in, is the second drug more effective than the first one. And the p-value is greater than 0.05. So we would say, I don't know, we would say we can't be sure. No evidence that the new drug is better. If we do best analysis, then we get the mean difference. It's minus because it's 1 minus 2, minus 1.59. We've got a credible interval, put all that information, and we're 94% certain that drug 2 is more effective than drug 1. So if I needed a drug to help me to sleep, or if I was prescribing a drug to help a patient sleep, I would be 94% certain that drug 2 is better. That might be a mistake, but there's only a 6% chance that it would be a mistake to prescribe drug 2 instead of drug 1. The best package actually produces more information than that, and this is one of the arguments that Krushka makes in favor of Bayesian analysis, that you've got lots more information. You've got means for both groups, you've got standard deviations for both groups, you've got a difference of standard deviations for the two groups. The best package does not assume that the populations are normally distributed. Instead, it uses a t-distribution. T-distribution has fatter tails, so it accounts for outliers. It works much better with outliers. So we use a t-distribution and estimate the number of degrees of freedom. Degrees of freedom, if the degrees of freedom is large, technically if it's infinite, then it's a normal distribution. If it's small, then it's not normal. So we've got a degree of normality. So down here at the bottom left, we've got an estimate of the degree of normality. And in this case, it's the degrees of freedom is about 30. We're looking at the log 10 degrees of freedom. That's about 30, which means that it is pretty well normal. It's not far off normal. So there's lots more information we can get out of the Bayesian analysis than just a p-value. So even for very simple questions, it still, I think, makes sense to try a Bayesian analysis and get this much richer output, different aspects of the data. So good. So yes, best and in general Bayesian methods produce much more information than frequentist methods. In wildlife ecology, there's been a renewed emphasis on modeling. Modeling is not new. It goes back to at least George Box in the 1940s. But we are really now putting more emphasis on models and different kinds of models which have which represent ecological hypotheses. So a renewed emphasis on modeling and model selection. Which is the best model? Using AIC or there are a few other information criteria to help us to decide which is the best model. The best model, meaning the one which makes the best predictions of new data. Bayesian methods, these are now very widely used in ecology. For simple cases, it's good because we get more information. For complex analyses, there are often things which you could not do in a frequentist framework. But they are, as we've seen, it's relatively simple to write a bugs model with all the different ecological bits in it that you need, and it's transparent. You can see what the model is doing. And then these complicated hierarchical models are relatively easy to program. It used to be the case that during Fisher's lifetime, Fisher maintained that Bayesian methods were just wrong, that it's an error and must be avoided at all costs. And in fact, it's Fisher who came up with the term Bayesians. He thought of it as a term of abuse. You're a Bayesian. Yeah, that was a term of abuse. But Bayesians have accepted that and said, yeah, sure, I'm a Bayesian. The fight that's now generally accepted that Bayesian methods are okay. There's nothing wrong with Bayesian methods. You do need Fisher's problem with Bayesian methods was the prior. You need a prior to use Bayesian methods, and Fisher argued that this is unscientific. 100 years later, we now have a lot more real prior information out there. There's a lot more research being done in the last 100 years since Fisher was complaining, and it's available on the internet. So if we want to know about the weight of giant squirrel, we go online and we find some estimates. We've got some prior information. So Bayesian methods are no longer taboo.